And spacetimes, yes.
Affine linking numbers and causality in spacetimes. So what is a spacetime? A spacetime is a Lorentz manifold. So it is not a Riemann metric, but Lorentz metric. And the vectors in this spacetime, they have the following possibilities, that it could be that v dot v is negative. These are the so-called time-like vectors. They represent movement with the speed less than the speed of light. If the v dot v is 0, these are null or light-like vectors. They represent movement.
Elements of x or tangent space to x?
Tangent space to x, yes. So v is in TPX. And there are vectors whose dot product with themselves is positive. These are space-like vectors. And they represent movement with a speed greater than the speed of light. So very romantic, but physically impossible. So the set of non-space-like vectors. So non-space-like vectors are those that are null or time-like. Forms a cone in the tangent space. And what may happen is that I can try to choose half of the cone continuously dependent on the point. If I succeed to do it, this is called time orientation. And space-time is a time-oriented Lorentz manifold. So it is not just a Lorentz manifold, it is a time-oriented Lorentz manifold. And the vectors pointing into the preferred half are called future pointing. Okay, so I would like to put the following two restrictions on the space-time. Condition number 1. I would like to prohibit time travel. So what is time travel? Time travel is a closed, non-space-like curve. So no time travel. So you cannot go into the future. I'm sorry?
Non-space-like curves means its tangent vectors are non-space, right?
Yeah, tangent vectors are not space-like. So they represent movement with a speed less or equal than the speed of light. So I would like to prohibit time travel, which means that I prohibit closed non-space-like loops. And the second condition that I would like to do is that I would like to prohibit no naked singularities. So let me try to explain what a naked singularity is.
Мне вот очень нравилось ваше условие существования поверхности Каши.
Это то же самое.
Ну вот это сейчас немножко переформулировалось, да? Потому что, наверное, сильнее, чем вот эти два. Или это эквивалентно?
Не эквивалентно, это эквивалентно.
Ну хорошо. Когда действительно, если эквивалентно, то можно дальше рассказывать. Понятно, спасибо.
Вот. No naked singularity обозначает вот что пересечение причинного будущего точки P и причинного прошлого точки Q компактны для всех P и Q. Is compact for all P and Q. So let me try to explain what is causal future of a point P. These are all the points that can be reached from P or into the future with less or equal than light speed. So causal past of Q, J minus of Q, is all the points from which you can get to Q going to the future with less or equal than light speed. So the intersection is this diamond or rhombus. So it naturally looks compact, but it does have to be, because maybe in my space-time this point is deleted. Then this intersection is not compact. So why would it be a naked singularity?
So
Because then what? Huh?
is this a picture in the tangent space or on the manifold itself?
This is in the manifold.
But the cones are in the tangent space.
The cones are in the tangent space, yes, but the exponentiation of the cone is in the manifold. The exponent. So it is a semi-Riemann manifold. So similarly, the Riemann manifolds, there is a notion of the exponential map, and the exponentiated cone is in the manifold. But similar to Riemann situation, the exponentiated cone does not have to be embedded. It can have self-dissection points. So I have this intersection, and what may happen is that I put an observer here in this vertex, and I put a particle traveling to the deleted point. Then information traveling with the speed less or equal than the speed of light can reach from all the points of this trajectory to the observer till the particle disappears. So now our observable physical universe, we have never seen a particle disappear. It doesn't happen. So this does happen. This is called a naked singularity, and this is exactly what I'm prohibiting. So what may happen, and what should not be confused with what I prohibited, is the situation where a causal trajectory, the traveling particle P, intersects the rhombus, but it goes through the reverse light cone of the point Q. So if this happens at this moment, there is a common light ray between the observer and the particle. So before the particle disappears, the observer can see the particle. Right, so naked singularity is when the particle disappears, but the observer does not see the particle disappearing. Does it make sense?
Mhm.
So there is a theorem of Giroch, Bernal, and Sanchez that says the following: that such spacetimes, which are called globally hyperbolic, so if you have a globally hyperbolic spacetime, then the spacetime is homeomorphic to sigma cross R. Where each sigma cross T is Cauchy surface.
А сигма ничего не говорится, какая получится.
No, it will be of codimension 1.
Но это может и быть и компактная сигма, да? Как
Да,
получится.
it can be not compact, yes. So what is the definition of a Cauchy surface? So you have this cylinder, sigma cross R, and the Cauchy surface is a submanifold such that each causal trajectory, so trajectory of movement with the speed less or equal than the speed of light, intersects at exactly one point. Okay, so what makes it a Cauchy surface is that every physically possible trajectory intersects this Cauchy surface at exactly the one point. So Geroch theorem is about C0 identification of the space-time and sigma cross R. Bernal-Sanchez theorem is about the C-infinity identification. So as you all know, there are manifolds which are smooth and homeomorphic, but not diffeomorphic. So Bernal-Sanchez strengthened the result of Geroch, and they proved that global hyperbolic space-time is diffeomorphic to sigma cross R. And they also proved that then you can assume that H sigma cross T is space-like, which by definition means that the restriction of the Lorentz metric to sigma cross I is Riemann. Does it make sense? Hello?
Yes.
Okay, so now assume that I have a light ray. So light ray is now geodesic, future directed. So since this is a Cauchy surface, the light ray has to intersect the Cauchy surface at some point, right? Because light ray is movement with the speed equal to the speed of light, and every non-space-like curve, so movement with the speed less or equal than the speed of light, intersects the Cauchy surface at exactly one point. So the same would be here. The velocity vector is not tangent to the Cauchy surface, but what I can do is that I can orthogonally project the velocity vector to the Cauchy surface. So I will get a non-zero vector. You can spend a little bit of time, you will see that the projection is indeed non-zero. So now what? Now I would like to say the following, that null rays, light rays, do not have a canonical parameterization. Because how do you usually do a canonical parameterization of geodesics? You require that you travel with the speed 1. So you renormalize the speed so that the speed becomes 1. But here the dot product of the velocity vector with itself is 0, so you cannot do it. The null geodesics are defined up to affine reparameterization, which means that t goes to a t plus b. For positive t, for positive a. So if you choose a different parameterization, the projection vector will multiply by a constant, by a positive constant, but the direction will be preserved. So what we get is that the space of light rays is the spherical tangent bundle of the Cauchy surface. Right, unit tangent bundle of Cauchy surface. But Bernal and Sanchez proved that you can assume that the Cauchy surface has a Riemann metric on it. So spherical tangent bundle is the same as spherical cotangent bundle, because the tangent bundle is the same as the cotangent bundle. And the space of light rays is the spherical cotangent bundle of a Cauchy surface. Now, what is a null cone? So null cone, we all know that it looks like a cone initially, and then it develops various singularities because the light rays can intersect. Okay. So, but in the space of light rays, the null cone is a sphere. Right? Why? Because this light cone is a cone over a sphere. So if I regard every point on the null cone as a separate geodesic, as a separate point, every geodesic is now regarded as a separate point, then this null cone is a sphere in the space of light geodesics. So this sphere is called the sky. So the sky of P, which we will denote as of P, is a sphere of all light rays through P. And jointly with Nemirovsky, we proved a bunch of theorems which say that Legendre and linking of the spheres completely determines causality. So Legendre and linking of two skies as PSQ determines causality. So what is causality? Causality just means that there is a causal trajectory between points. So you can get from one point to another without exceeding the speed of light. So this is a rather deep result, but today I'm going to speak about a softer version of this approach, which we were doing with Yulia Rudyak. So here what I would like to do is that I would like to observe that the space of light rays is the spherical cotangent bundle of a Cauchy surface of sigma. Now, if sigma is m-dimensional, then the spherical tangent bundle is 2m minus 1 dimensional. How about the sky? So the sky is a sphere which is of dimension m minus 1. So if I give you a laser point and I ask you to point in the sphere of all directions around you, in your usual world, you can point it to a sphere, two-dimensional sphere of directions. This is the sky. For our space-time, the space of all light rays is 5-dimensional. So I would have two-dimensional spheres linked in the 5-dimensional manifold. So the dimensions are what? The dimensions are that 2 plus 2 plus 1 is equal to 5. This is exactly the dimension where the linking number should be possible to define. In general, what we will get is that we will have that m minus 1 plus m minus 1 plus 1 is to m minus 1. So this is the situation which has nothing to do with the dimension of the space-time. This is always the case. That the sum of the dimension of the skies of 2 points plus 1 is the dimension of the space of light rays. So this is the situation where linking number should be possible to define, but there is the following problem. That if you look at the Cauchy surface, and assume for simplicity that your point P is located on the Cauchy surface, then the sky is a fiber of the spherical cotangent bundle. And it is never zero homologous. So the fiber of the spherical cotangent bundle is not zero homologous. So the usual linking number is not defined. Right? But what you can do is that you can recall that if you have a linking number, then it possesses the following property, that if you pass through an intersection point, then the linking number, when you pass in the positive direction, increases by 1. Right? So if you pass through a double point of a link in the positive direction, the linking number increases by 1. Does it make sense? Это по ошибке. So what you can do is that you can define the usual linking number in the following strange way, that you choose a trivial link, and you choose a link where you want to define the linking number. And you consider a generic homotopy between the trivial link and the link where you want to define it. So this homotopy involves passages through double points. So this is a positive passage, this is a positive passage. So here the linking number was 0 because this was a trivial link. So here the linking number would have to be +1 +1. So can you do the same trick to define the linking number in general, right? And that I now no longer have a trivial link, I just have some link which I declare to be trivial. So my link components do not have to be zero homologous or zero homotopic or anything like that. They're arbitrary. I just choose a link in a given homotopy class, and I declare this link to be most trivial. For this most trivial link, I define the generalized linking number to be 0. And then if I want to define the linking number on some arbitrary link, I do a homotopy of the trivial link to my link, and I count the number of passages through double points with sides. So it seems like a very plausible definition, but there is a problem because maybe you have a different homotopy. For a different homotopy, the number of passages through positive double points would be not 2 but 3. So then the definition does not make any sense. So this is a problem, but jointly with Yuliy Rudyak, we showed that this is actually very rarely a problem. So we showed that in the case of STM, this affine linking number, which I was defining a few seconds ago, is integer valued, well-defined invariant, unless M is an odd-dimensional rational homology sphere. Right, so usually rational homology spheres are good. For us, they're bad because you want the linking number to be integer valued. So if the manifold M, the Cauchy surface, is an odd-dimensional rational homology sphere, then we have a bad situation, and the linking number is not integer valued. It takes values in Z mod M. But the only really bad situation is when the affine linking number takes values in Z1, so it is a trivial group. So this happens only if M is a homotopy sphere. So we define this linking number. So what is the physical interpretation of this number? So assume that I have two causally unrelated points, for example, on the same Cauchy surface. And what I do is that I look at the light cone of the point P. So it is singular, so I should probably redraw the picture a little bit. they look at the causal trajectory of the point Q to somewhere inside of the light cone. So this would be Q tilde. So the theorem that we proved with Rodiak is that the affine linking number of the sky of the point P and of the sky of the point Q tilde is the number of times an observer traveling from Q to Q tilde sees the light of P.
Can you restate it in topological terms?
Huh?
Can you restate this in purely topological terms?
Sure, it is the intersection number of the relative homology class of the path from Q to Q tilde and of the null cone of P. Right, if you have two manifolds,
Null cone is already some geometric condition.
yes, but it is a manifold as well, singular manifold. So for two singular manifolds, you can look at the intersection number.
Does this hold when m equals 1 for one-dimensional manifolds?
For one-dimensional manifolds, it does not work. No, sorry. Starts to work from dimension 2.
So it is wrong, even modulo 2.
What I have no idea on this. I mean, maybe it is right, maybe it is wrong, but our theorem was formulated, started from dimension 2 and above. See, for dimension 1, the sky is not connected. It is 2 points.
Yeah, but anyway, you can define the linking number between two zero-dimensional spheres.
Probably, but I mean that I'm not ready right now to discuss it because I could say something wrong.
Okay, the reason I'm asking is because in this case you can actually draw something. How this maybe it's difficult to compute this linking number of zero-dimensional spheres, but it's easy to draw the zero-dimensional spheres, and especially this sphere. Yes. For one
Yes, but here it is also not hard. You draw the null cone, you look at the path from Q to Q tilde. This path intersects this null cone generically at the points where the null cone is immersed. So you look at the orientation of the intersection point, right? I mean that the first vector of the frame is the velocity vector of the path from Q to Q tilde. And the second part of the frame is the orientation frame of the null cone. So this gives you the orientation of the ambient spacetime. It is either positive or negative. This gives you the intersection number. Right? So if you believe that the affine linking number is equal to this intersection number, then what happens when your observer passes through the light cone of P? So at this location, there is a common light ray between P and the observer. So the observer will see a light from P. So this is the clarification of the theorem that I formulated in physical but not geometrical terms. And finally, so the final piece of the puzzle is that if time-like sectional curvatures are greater than 0, then a affine linking number is non-zero. Exactly if P and Q are causally related. Right, so let me try to say a couple of words about this fact. So usually when you have a Riemann manifold of negative sectional curvature, then the exponential map is an immersion, right? But here the only exponential we care about is the exponential of the null cone. And in O'Neill you can find a theorem saying that if the time like sectional curvatures are positive, then the exponential of the null cone is an immersion. So this would mean that all these intersection points are of the same sign. So you could not have +1, -1, and so on. So the number of intersection points will actually be equal to the linking number, and it will be non-zero exactly if the 2 points are causally related. So this affine linking number would completely determine causality. And I think that this would be a good place to stop, because I'm out of time.
Ну, спасибо большое, Володя. Значит, какие будут у нас возможности?
Thank you. Any questions?
Володя,
Are there any questions? Да,
Why-
какие вопросы?
two embeddings of a ascend disjoint ascend to n plus 1 manifold, a relative embedding which you can call linking number of two embeddings, right?
Yes, it is a affine linking number because it is affine because of the following reason.
Yeah,
That
I know why.
in order to figure out where the affine linking number is zero, you have to choose the most trivial link in your homotopy class.
I would suggest you look at Hudson's papers for Hudson's book where such an invariant was defined. I will try to help you with references.
Sure, but I think that Hudson and Gluck were later than us.
Sorry?
The thing that the Gluck paper was after our paper. Our paper was written rather long ago.
I mean Hudson's paper of 60s.
Ah, sorry, no, my bad.
Actually,
I thought that you're talking about Hermann Gluck.
my second thought, of which I'm not sure, is that in Saveliev's book on three manifolds, he did consider linking numbers for links not null homologous. I'm not sure about that reference, but at least Saveliev is easier to check.
Okay, thank you. Thank you very much, Heidi. Okay, are there any other questions?
Yes. Can
Yes.
you draw this linking? How this linking occurs for causally related points? Because I don't understand it geometrically. I heard it several times from you, many times, but still I don't have a picture in my mind. Can you draw some picture for a statement?
So assume that I have the simplest possible situation. So I have a Minkowski spacetime and I have 2 points, one inside of the other. So this is the Cauchy surface. Then the intersection of the null cones looks as two concentric spheres. Yes? So they are co-oriented outside because the orientation is the projection of the velocity vectors of the light rays.
Sorry,
So
what is the red picture?
the red picture is this intersection of the null cones with the Cauchy surface.
Yes.
Now, the unlinked situation is two circles which are separated from each other. How do I see that this is linked? So I would like to do the following. I would like to choose this circle and I would like to drag it outside. But when you drag it outside, there will be a moment when you get the so-called Arnold's dangerous tangency. So your two circles will be tangent, and the direction of the co-orientation will be the same. Right? But now our linking happens in the unit tangent bundle. So when you have Arnold's dangerous tangency, you exactly get double point of the link.
Okay, now I understand. Thank you.
So when you separate this link to the trivial link, you have one passage through a double point. Okay. So are there any other questions?
Okay, let's thank the speaker. If there are no other
Thank
questions.
you. Thank you, Sergey, and Petya, happy birthday.
Спасибо. А все-таки можно прояснить, вот, значит, там было сказано, что если есть поверхность каши, то, значит, вот условие, что есть это дедушка, который там что-то там с внуком, и дальше эквивалентно, хорошо. Теперь условия поверхности каши в трехмерном случае, значит, гарантируют безопасность от того, что мы попадем в экзотическое четырехмерное многообразие. Это было там, ну я, может быть, что-то неправильно понял, но у вас такая была теорема с Немировским.
Да.
Вы применяете. Но это замечательно, да? То есть вот это вот опасение, которое высказывал Сергей Петрович Новиков, что не может быть пространство-время экзотическое, оно как бы снято, да, в вашей теории. То есть...
Ну, не совсем, потому что мы его сняли для компактных поверхностей каши размерности 3, то есть четырехмерных спейстаймов с компактной поверхностью каши. Или мы его сняли для стягиваемых спейстаймов с любой поверхностью каши, любой размерностью. Но есть еще открытый случай, когда у вас поверхность каши не компактная и трехмерная. Тогда мы не умеем доказывать то, что нет экзотических гладких структур.
Ну, казалось бы, если она не компактна, то это так обычно и бывает, что... Ну, это типичный случай. То есть, как бы вы сняли, но в таком важном, в частном случае еще пока открыта проблема. Ну,
Да-да.
если стандартное пространство Витковского, оно же открыто, но поэтому как бы,
нет,
наверное...
в стандартном пространстве Минковского оно стягиваемо. Мы сняли в двух случаях.
Я понял, да, я прослушал. Спасибо, да. Ну хорошо, ладно, стало как-то спокойнее, что мы это самое уже там сможем это все изучить, потому что если бы оно было экзотическое, то шансов бы не было никаких. У нас была бы физика, которая зависит от того, как мы напишем оператор d по dx. Ну, значит, как бы можно расписаться в своей полной, значит, в своем бессилии, потому что мы не можем такую физику изучать, которая зависит от того, как мы будем матанализ изучать. А тут, значит, вы сняли это и тем самым вселили оптимизм. Ну, во всяком случае, в моем понимании, очень ценно. Вот, ваш результат исключительно ценен. Вот. Ну, конечно, вот эти зацепления жанровые, они требуют более пристального внимания, но то, что вы вот сейчас вот сказали, Сережа спросил, было действительно понятно. Но вроде как я это и раньше понимал. Ну так вот, если прогресс по сравнению с работой, которая вот с Рубиком была, это же давняя работа.
Есть, да, это давняя работа, то есть реальный прогресс это как бы наша работа с Немировским, просто, ну
да, там, конечно,
был запрос от Сережи, чтобы по возможности доклады были связаны с тем, что делаешь. Ты как бы занимался linking numbers, поэтому я решил, что это более в тему. Ну и такой другой прогресс, это вот то, что я пытался Ване Денникову сказать про нашу новую работу с Рустамом Садыковым, который еще нет в архиве.
Сейчас, Ну все, да, я задал вопрос. Спасибо.
Да-да, спасибо.
Спасибо за доклад.
Мгм, спасибо. Еще раз с днем рождения.
Okay, so it's approximately time for the next talk.
Спасибо.